So we'll get started. So welcome everyone to another OCP Tap session. And let me just quickly check what number is this? I don't know. I'm getting obsessed with the numbers. So yeah, this will be called number 85. Great. So as usual, we start with the format where we introduce our speaker. So our speaker is Seth, and Seth has been an active leader at the forefront of electronic trading for over 23 years and has deep sales trading and technology and consulting experience and a history of technology vision, particularly in the area of FPGA implemented network attached compute with more than 12 patents, including the invention of a multi-patented FPGA order processing technology proven in the field since 2010. In Morgan Stanley, Japan, Seth headed program trading before establishing the electronic trading services business and later heading the business throughout Asia. At Nomura, Seth established and headed the quantitative prime services business, played a key role in post-acquisition integration of Lehman Brothers, and was responsible for electronic product management across Asia. So today's talk is about ÜberNIC. So ÜberNIC is basically a FPGA-based NIC. And I'm very excited about it because it has PTM and PTP support, but I should be also excited about the CXL Type 2 and Type 3, which it got. And I think we also have White Rabbit on it. And so without spoiling too further, let's give the floor to Seth.
Take 15 more seconds as I walk back with my coffee.
Sure.
Thank you. Okay, it's okay. I'm back.
You get it.
Yes, I get it. We got to work on Ahmad's reading of scripts here. That sounded terribly unnatural. Yes, exactly.
Very unnatural.
I think you should call Mr. Zuckerberg and ask him to provide one of those to you.
Okay, let's not.
Yeah, let's not go there. Okay,
it's all recorded. So Seth, I just want to.
Oh, sorry. Yep, apologies. Okay, good to meet all of you. Again, a few of you I think I know. We LMS have become more and more involved in the precision time community over the last couple of months, and we will continue to become more and more involved as we move forward. So we have been working on an FPGA-based general purpose network adapter called ÜberNIC, as some people know, with the Umlets, and there's a reason for that. We're not trying to take a play on the ride-sharing app. And within this, what we are really trying to do is solve a number of different problems. So as we know, FPGA-based network capabilities in financial services have really focused to date on supporting high-frequency trading, right? We take, despite my background, we take a slightly different view of how these types of tools can be useful, not just in financial services, but quite beyond financial services. So I'm going to talk a bit about the overall what ÜberNIC is, and I'm just going to walk through the standard deck that we walk through. But clearly for this community and audience, I'm going to really focus in on precision time, and I'm going to talk about some things that we'll be talking about next week at OCP in San Jose. There's also a financial services series of conferences called Stack Research. The first fall event is in New York next Thursday. We will also be talking about some of these things there, and at subsequent conferences in Chicago and London for Stack. We will be at ITSF in Antwerp, where we will have a live demo of ÜberNIC with a number of features, including some of the precision time capabilities. And ultimately, we'll end up in Denver in November at SC23, also demoing all of the capabilities. But what we're really focused on here. So general purpose Ethernet adapter, we are implementing the network stack fully in the FPGA chip. So MAC PCS, Ethernet, IP, TCP, UDP, ICMP, IGMP, ARP, VLAN, BGP are all implemented inside the FPGA chip without any component of the network stack running in software. Now, of course, we have to move data back and forth across the PCIe bus to support the host, but the idea has been to try to create the FPGA chip as a separate compute realm, not simply an offload resource, which is the way it's been largely used, at least in financial services, for quite some time. And we see it as a separate compute realm. And so to really deliver on that vision of it being a separate compute realm, we need to make it a separate compute realm. And so it's, and its own independent network stack moves in that direction. We work very, very closely with Intel on this, and have been for, at this point, almost 2 years. We also work with Bitware from a board manufacturing perspective. So you are literally looking at a prototype board. I'm also going to do a little bit of show and tell. So it's not just a picture, it's real. There are 2 different boards, and I'm just going to describe some of the overall capabilities of each of the individual boards, and then get into the actual functionality features. So they're 2 different board designs. They are both single slot. The smaller board that you see here is clearly half height, half length with a single QSFP DD. There's a bigger board that right now is plugged in and doing something, so I can't show that to you. That other board is still a single slot, but it is full height, 3/4 length, and it has 2 QSFP DDs. This particular board has 16 gigabytes of soldered DDR. You can see some here, and there's more here underneath the heatsink. The bigger board implements 2 SODIMM sockets, and can support, therefore, 64 gigabytes of memory. The reason for the SODIMMs rather than normal DIMMs is if we plug in a normal DIMM, we go perpendicular, and then that length makes it too much to maintain a single slot. And we wanted to make sure that we were maintaining within a single slot. Given today's technology, we think it's sort of inexcusable to waste a PCIe slot simply because we can't package things in a creative way. So that's some of the reasons behind the choices that we've made. We've tried to build something focused on meeting a wide number of use cases. Ultra low latency and ultra high capacity and ultra consistent performance that's demanded in securities trading on one end of the scale, and then ultra high capacity data moving for hyperscalers on the other end. Today we support 10G. We're not live yet. We're still in the final engineering phase before we start rolling out sample boards to close partners. Today we support 10G. We have already started working on 25G. We have an operating version of that at the moment from an Ethernet level with some runt TCP payloads. We've already been able to create 25G with forward error correction and without forward error correction. And particularly for financial services, without forward error correction for short range connectivity is very important because it's about low latency, not long range connections where we actually have to make sure that the communication path and the data is not being disrupted in any way. From a link speed standpoint, we will also implement support for 1G, 40G, 50G, 100G, 200G, and 400G, all from a single board. So again, securities trading on one end, hyperscalers on the other, everything in between. This is already the world's first PCIe 5 network card. It's also the world's first CXL compliant network card. I'll show you a slide in a minute that talks about some of the performance. We can support significant fiber density from the QSFP-DD. So for 1, 10, or 25G, we can get 8 fiber pairs in a single QSFP-DD here, or the board with 2 QSFP-DDs, we can obviously then get 16 fiber pairs. I've already mentioned the fiber density. And now we start to move into, I'm trying to move us forward into what we all really care about here. So then we get into the other capabilities that we get because it's an FPGA chip, right? It's not an ASIC with a software network stack. It's an FPGA chip with a hardware network stack, and we can do a lot of stuff because it's programmable. So we do timestamping of all data that is received or transmitted. Pick a bit position, and we can timestamp at that specific bit position. We can timestamp at multiple bit positions. You can't really do that with other solutions. We can do internal what we call internal p-capping. As data is received or as data is transmitted, we can actually dump that into onboard memory and generate real-time p-caps as data is flowing. And then we have to offload that. The memory is ultimately limited. We have to offload that either across the PCIe bus or across some of the fiber. But the benefits of this are quite significant. So at least in financial services, there will very often be top of rack timestamping and packet capture devices. They consume rack space, they consume electricity, and at the end of the day, particularly for timestamping, they're actually not accurate enough. So there's always going to be some degree of fiber between the actual device that's receiving and transmitting and that top of rack device. So at least a meter, maybe two. If there's a direct connection, very often there'll be a switch. So we end up with a significant delta in the timestamps that are generated by a top of rack device versus the actual as received or as transmitted timestamps. So the benefit of what we're doing here is that we will be able to provide perfect as received, as transmitted timestamps, and we will therefore allow people to turn off and disconnect and remove these other top of rack devices, saving space and allowing people to reuse that space for other purposes if they want. And now we get into the meat of it. So if we're going to do timestamping, obviously we need accurate timestamps. That's critically important. So we implement a PPS in, we implement a 10 megahertz clock in, and for a friend, I'm not going to call out his name, but there's been a long-standing question about us supporting PPS out, which initially is not in the engineering sample boards that we have here. But we are implementing a PPS out on a slight respin of our boards as we go into production. So there will be a PPS out, but not two daisy chain things. So I'll come back in a minute and explain what we're going to do with PPS out. Of course, we support NTP, PTP v2. PTM, I don't want to talk about too much because we're going to talk about that. I'll talk about that with a guy named Dave Sage at OCP next week. Ultimately, PTM, precision time measurement, which is implemented in the new 4th generation Xeons and is also implemented in the Agilex I-Series FPGA chips that we're using, provides as I think everybody in this call knows, a method of transferring a time value from the NIC into the host to update the real-time clock via the PCIe bus as a hardware mechanism, as opposed to a software update. But ultimately, the hope of PTM is not really what it's delivering. So there are really two good things you can say about PTM. Plugging in a board with PTM out of the box, you can get to ultimately, after we update the host real-time clock, and we compare that post-update time to the time in the NIC, which of course is the time in the Grandmaster and GPS. Post-update, the host real-time clock is at best plus or minus single-digit nanoseconds. So really, we've got at best sort of a 14 to 15 nanosecond window of accuracy. At worst, it's an 80 nanosecond window of accuracy. So really, it provides what we can do with PTP, although we have to go through a lot of effort to achieve that with PTP. So the numbers that I'm just mentioning are literally plugging this in, no PPS of any kind, just snap a time value, use the FPGA chip to then manage time, and then with PTM, we're transferring a time value once a second. So We get to what PTP does, but with, as we sort of talk about in the presentation we do next week, sort of like, look, Ma, no wires. So we can get there with relatively little effort, which is a good point. The other point is, because of the hardware nature of the transfer, PTM is really not susceptible to load-induced performance degradation. So you'll see some charts in the presentation next week. We did testing with a server, and we went through iterations of doing a series of tests with literally no load on the server, all the way up through completely loading 54 of 56 cores, so 96% utilization. We also did 25%, 50%, and 75%. And as you'll see next week, when you look at the charts, you can't see a difference. So there's nothing that gives away by looking at the PTM variances at 96% CPU utilization. The charts essentially go look exactly the same as 0% CPU utilization. So that's also a good thing that can be said about it. But for what we're doing, because we are implementing White Rabbit in ÜberNIC, so this will be the first standard hardware NIC to support White Rabbit, PTP and PTM are really not going to be good enough, right? If we're in a world of at least double-digit picosecond timestamps in this, then nanosecond level synchronization with the host is really not sufficient. So we've come up with a different way to update the host. To be fair, I want to make sure that I'm acknowledging the great relationship and partnership that we've had with both Ahmad and Julian over the last couple of months. We've all brainstormed this problem together. They have, and Julian has developed, and I think Julian presented a couple of weeks ago on PFM, precision frequency measurement. But ultimately, we have a similar goal. The devices that we're building are going to incorporate White Rabbit time. And the devices that are connected to that need better time synchronization to this much more accurate time. So Ahmad and Julian are going in one direction for updating pluggables. We're going in a slightly different direction for updating the host. Part of the reason for that is on the host side, to update the host, if we want to do anything with the actual PCB, we have to get motherboard manufacturers to agree to that work. That's a bit of a heavy lift. So we're sort of viewing this as a two-stage effort. Stage one, which I'm going to describe in a minute, is a next step. And ultimately, if we can demonstrate that there is, sufficient enough interest in the industry that generates revenue for board manufacturers, then hopefully that will provide enough justification to go to the next, and I think in our minds, the ultimate step as we can imagine right now. So what we're going to be doing, I think everybody on this call is aware that some of the CPUs, particularly the Xeon 4th Gen, have 2 TGPIO pins on them. Everybody knows that? Yes, thumbs up, thumbs down. Everybody's muted and nobody has their camera on, so I can't see. Anybody have any questions on that point, or can we just take it as an assumption that everybody knows? Okay. I take silence as agreement. So in the past, there's been discussion about using the TGPIO pins to have the CPU generate an outbound PPS signal. But those pins are bidirectional. So what we're going to be doing is, this is why we need a PPS out. So there'll be a PPS out on this, and then we will connect a cable from ÜberNIC to a proper connector on the motherboard, which will ingest the PPS signal and ultimately deliver it to the TGPIO pins, aligning the host clock to ÜberNIC, to the Grandmaster, to GPS. There's a lot of work involved across our company, LMS, across the board manufacturer, Bitware, We have, I'll leave the motherboard manufacturer for last. On the Intel side, as they have to do work with the driver to actually ingest the signals. And then I want to specifically call out ASRock, who have bent over backwards to be cooperative and be forward thinking in doing this. So they are taking two different production motherboards and they're actually respinning them to include proper plugs on the motherboard so that we can connect without an alligator clip, without scraping off protective covering and then soldering stuff. This will be a production solution using production hardware. And the best part about it is ASRock has committed to having both a Xeon 4th generation workstation motherboard and a dual socket Xeon 4th generation server motherboard respun within this calendar year. They're actually saying the tail end of November. I think we should haircut that just a little bit. So there will be a production grade solution delivering this capability within this calendar year. Even better, Ahmad, did you see the email?
Yes,
okay.
yes.
Yeah. So even better, ASRock is actually sending us the server motherboard, and we'll have that to us next week. It doesn't have the proper connectors, so it'll be a bit of a more manual one-off mechanical connection, hopefully. I hope we don't have to get Julian to do another flex PCB and somehow figure out how to make that work. But our goal is to be able to have a working demo, hopefully by ITSF, we'll see. Obviously, there's driver work that needs to happen. So this whole idea has gone from concept to basically implementation in what, 2.5 months? Again, with production hardware coming relatively soon from ASRock. We are also working with Jabil. So Jabil has already modified their BIOSes to support configuration of each of the separate TGPIO pins. And we're waiting for a map from them as to where the traces actually are on the motherboard. And then we'll start to see what we can do with that. Ultimately, we are optimistic we will get Jabil to also make a slight respin and include proper connectors. We are also in discussions with Supermicro to do the same thing. And hopefully, if we can get enough of the manufacturers on board quickly enough, then other manufacturers will feel the need to do the same thing just to catch up. I should also mention ASUS. ASUS was really the first firm to enable the TGPIO pins in their BIOS, but there have been a few challenges trying to make that work. And there's a separate CXL related issue with the ASUS motherboards that's preventing us from really working with those motherboards for the moment, because CXL is a really important part of what we do. And it's not even if we can get this working on an ASUS, the time working on an ASUS motherboard, if we can't get CXL working the way that we want it to, we're not going to be able to do much with the ASUS motherboard until it provides better support for everything that we care about. So from a precision time standpoint, there's an awful lot that's coming to this new product. So again, first NIC to support PCIe 5, first NIC to support CXL 1.1, first general, commercially available, standards compliant, full FPGA implementation of a network stack, first White Rabbit support in general standard hardware, first support of PTM in general standard hardware, PTM v2, etc. Any questions on any of that so far? Okay, a couple of other comments related to White Rabbit and CERN. So I'm based in Zug. I am 2.5 hours by train, 3 hours by train east of Geneva. So I was actually at CERN a couple of weeks ago, spent the entire afternoon with Amanda Maj and other people. Wonderful group of people. can't get enough of them, honestly. And I think, as most people know, CERN is starting an official White Rabbit collaboration. We got the... Whoa. Shiga-san, you had a comment, question?
Yeah, I have a question. So you mentioned that there will be a PPS out pin or cable connected to the motherboard CPU eventually. And my question is, so is that to control the clock or oscillator of the motherboard? And I'm not sure what can be done on the motherboard side and what cannot be done easily. And so my question is, if the goal is to control to align the oscillator or clock of the motherboard clock to the ÜberNIC, then can't you just use the PTM data to sort of steer the clock on the motherboard? And so I guess my question is, why do you need the physical cable to the CPU?
Yeah. So what we've seen with our testing, sorry, apologies. Shiga-san, are you based in Japan?
I'm sorry. I'm based in Bay Area. I mean, I work for NICT Japan, that's Japanese government lab, but I am physically in Bay Area, so I meet with Ahmad and Julian oftentimes.
Understood. Hopefully I'll be able to meet you next week. So, すみません。ちょっと、私は27年間、日本に住んでました。それだけ。
すごい。
Sorry,
Yeah, you
guys.
mentioned NRI and so on, so yeah, I was
Yeah,
wondering.
yeah, I'm looking forward to meeting you. Sorry for that little
So you're coming to the OCP Global Summit?
Yeah, I'll be there next week.
That's great. Okay, great to see.
Yeah, so the specific answer to your question is PTM is not accurate enough. It just isn't. We've done an enormous amount of testing. We have actually been able to correlate that CPU temperature, has a direct impact on PTM performance and accuracy. You'll hear us talk about that in the presentation next week. But all of our efforts have only been able to result in, at best, as I said, sort of 7 nanoseconds up, 7 nanoseconds down post-update accuracy. And that's just not good enough when we have White Rabbit. Ahmad, are you guys comfortable talking about what you've seen with your PTM testing?
Yeah, I mean, so just to clarify to the rest of the audience, like, I mean, PTM is in its infancy, and this precision that you're talking about, like, again, that comes basically from the White Rabbit, and then you want to funnel it further in the system. Yes, of course you need this, but I mean, this doesn't. Just want to clarify this. We are all on the same page, that it doesn't undermine like what PTM's value is. Like, PTM is growing, basically. Yeah, but for now, because you want to be ahead than the game, you're basically using the TGPIO.
Correct. And then to also answer your question, in terms of the ingestion and exactly how that's going to work, I can't actually answer you, but we do have a call in about 7 hours with Intel to start working through the details of what the CPU is going to do after it ingests the actual signal. So I'll have more information on that next week.
Okay, great. Thank you.
Our part in this is sort of, the NIC to motherboard side, and I think in conjunction with Ahmad and Julian, sort of tag teaming on motherboard manufacturers to get them to do what we want them to do. Bitware handles the FPGA board itself, so the signal is actually going to be at 8 gigahertz. So we'll have a really, really sharp edge. And then Intel owns the driver and the post-ingestion processing of the signal.
Thank you.
Does that answer your question?
Yes, thank you. And
Cool.
I also see another hand by Bilal. Bilal.
Yes. Please, just go ahead.
Hi. Yes, my question, this is Bilal speaking. My question is about how many ports does this NIC board has? 1 or more?
How many network ports?
Yes.
Yeah. So if we're talking about 1, 10, or 25G, in this QSFP-DD, we can put a 40G transceiver and we can break out to 4 fiber pairs, or we can put a 200G transceiver. I don't have one of them here. So we can take what is basically a PAM4 transceiver. They're sort of custom made by both Molex and FS.com, and we can get them to emulate NRZ. And then with a 200G transceiver and the proper cable, we can actually output to 8 fiber pairs. So again, for 1T, for 1, 10, or 25G, we can squeeze 8 fiber pairs into this one single connection. And then, as I said, we have a slightly bigger board that has 2 QSFP-DDs. So then with that, we can have 16 fiber pairs. As a point of note, AMD Xilinx released a very specialized FPGA board 2 weeks ago that's very focused on very, very, very low latency securities trading, where data comes into the FPGA chip and never leaves. The strategy looks at the data in the FPGA chips and then sends orders. That board that AMD has released has 4 QSFP-DDs in this slot, which means basically the entire space is taken up by QSFP-DDs. So that board can support 32 fiber pairs. However, we do question it because each of these consumes 10 watts of energy and then is generating a lot of heat. So with 4 of them, the entire end of the bracket is covered. There is no airflow exit. And we've got 40 watts of energy that's venting into this now restricted space. So we don't think that's the best solution. We've tried to achieve a balance of fiber density, cooling efficiency, and deployed memory capacity to have a rational product that's focused on more general purpose capabilities. We are not trying to build a product for 5% of financial services use cases, which is really what ultra low latency, high frequency trading is. Did that answer your question?
Yes, thank you. Maybe one short question about how many timers this pass, which can be synchronized to this PHC clock.
I'm sorry, one more time?
How many timers does this NIC can support, or is this seen as a feature support? Number of timers.
I'm not quite following your question from the standpoint of number of timers. So there are a number of different clocks on the board in the chip that we use for managing the FPGA itself, managing internal clocks. So I'm not quite following you when you mean timers.
In the context of PTP, time synchronization, so you will have this PHC clock which you will be synchronizing. On this NIC, is there any support for additional timers, so more than one timer?
In theory, yes. So
I think this is more like virtual clock, right, Bilal?
Yes, my question goes in this direction because if you go virtual clocks, then we will need more than one timer.
Yeah. Seth, I think you're muted. Seth, you're muted.
You're muted.
Seth, you're muted. Seth, you'll be muted. You're being muted. Is he muted?
But Ahmed, I think you got my question right until he unmutes
himself. I mean,
okay.
Seth, you're
muted.
My
question goes in this direction.
Someone tell Seth.
He's not muted. It just the audio doesn't work well. If he's muted, he has a muted sign showing up.
No, I mean, from his end, probably the microphone is something.
Yeah.
Let me see. There's no message on this. I mean, sorry.
There should be a chat board. There should be a chat.
Yeah. Hello. And oh, there's nothing here. You're muted, Seth. Okay. So we
I
didn't
apologize.
hear,
No,
we
sorry, that
didn't
was
hear
that.
the last 2 minutes, I'll say, like basically answer.
Yeah, I'm sorry, that's my fault. My iPhone took over the Bluetooth of my headset. I just realized. So I was talking to my iPhone, not you guys. Sorry. So thank you, Ahmad. I hope Ahmad successfully answered the question, since I clearly did not.
No, go ahead, go ahead. You can.
No. I think you got it. Or I assume you got it. So no, ultimately what I was saying was that we already use the FPGA chip itself, and we set an FPGA clock counter cycle, so that we just cycle through clocks and we know what the frequency is, and so we can calculate time using that. We already do that and have been doing that from the beginning of our company 4 years ago. We'll continue to use that for some parts of what we're doing. But the bigger question on our side is whether the FPGA chip, the limited granularity of the clock cycles, and in particular, the heat generation, whether that will, it's clearly going to have a negative impact on accuracy. The question is whether we can live with that negative impact, or whether that negative impact is too great and we actually have to add a separate precision time management ASIC onto the board to actually handle all of the precision time. We don't know right now, and we'll see what happens. But we're cautious that the FPGA chip in the longer term for the precision that we care about might not be the right solution. Other questions at the moment?
So what would be the ideal thing? Like an ASIC?
I think, some of the time chips that that Julian's been able to find, and I look forward to meeting the guy from Renaissance and talking to him. Certainly Bitware from the board standpoint is perfectly willing to try to find room for a 10mm by 10mm chip. It's going to be a bit of a challenge on this board, but the bigger board, I mean, we could play ping pong on the bigger board. There's so much empty space on it. So we've got to implement this, the PTM, what we're calling PTM v2, get White Rabbit implemented, and then we'll be able to assess where we stand at that point.
Excuse me, when you say bigger board, does that mean like a double slot?
No. So the bigger board, I'll sort of turn the camera towards it. So the bigger board is still a single slot board. I don't know if you can see it over there. There's a little red light. It's still a single slot, but it is full height and 3/4 lengths. That's what I mean by bigger board. So it's just a bigger physical PCB. We needed that, we were not going to squeeze 2 QSFP DDs on this board. So we needed a bigger board for the QSFP DDs. We also wanted more memory density. We did not want the memory soldered. So we wanted SODIMMs. We're not going to get SODIMM sockets on this PCB. So again, there is, this is half height, half length, single slot. The bigger board is still single slot, but full height, 3/4 length.
Thank you.
You're very welcome. Other questions? Okay. I'm going to jump to the next slide so everybody can start to see what latencies are. Again, our primary initial marketplace is financial services. So being able to accurately understand the latency of the platform to receive a frame at the transceiver, process that frame through the network stack, and in our model, because the network stack is in the FPGA chip, pass that payload across the PCIe bus to the host. In this case, a user space, what we call tick-to-trade application, which receives that payload and immediately transmits it back out across the PCIe bus through the network stack where the headers are constructed, and then out the transceiver. So we measure latency by looking at the bit position immediately following the start of frame delimiter on the ingest side, and the same bit position on the egress side. We are able, different product that we built, an FPGA-based tool to control testing and measurement. We call it TASER, Testing and Simulation Rig. And that allows us to send different types of protocols, UDP, TCP. We can control the payload size. Critically, we're able to control the interframe gap with great precision. So by varying the interframe gap, if we have a certain number of frames that are being transmitted and we make the interframe gap smaller, we're creating higher throughput rates. If we make the interframe gap larger, we're creating lower throughput rates. So we're able to simulate a variety of transmission rates into a target and then measure the total I/O latency and achieve or have the numbers, which I'm going to walk through here. So as I mentioned, ÜberNIC supports PCIe 3, 4, 5, CXL, and of course it can also support intra FPGA activity. All of that is reflected here. As I think some people will recognize or will know, from a securities trading standpoint, the traditionally used low latency network card and network stack is a product called the X2522. It's an ASIC-based network card that was originally produced by Solarflare and is still produced today by Xilinx, as Xilinx, of course, acquired Solarflare in 2019. That product uses a software network stack, or a number of different possible software network stacks, but the most performant of those software network stacks is something called TCP Direct. As a frame of reference here, the X2522 using TCP Direct has a 95th percentile latency on the same platform that these testing results were achieved on. The Solarflare product has a 95th percentile latency of 1.26 microseconds. Again, full I/O, 64-byte UDP payload, so 110-byte frame, received in the network stack and then processed. And of course, there's a big difference between our product and Solarflare. Our product is a hardware network stack. Solarflare is a software network stack, meaning in the software network stack model, we've got a 110-byte frame being transmitted across the PCIe bus, in the case of the X2522 using PCIe 3. In our model, particularly with CXL and PCIe 5, but applicable everywhere, because we have the network stack and the FPGA chip, we're receiving the 110-byte frame into the network stack, but we're processing that. And so the only thing in our model that's going across the PCIe bus is actually the 64-byte payload. So we get more efficient use of the resources on the host side by handling the processing this way. Other benefits are, particularly in a data-intensive environment, where network processing is very important, people would, with a software network stack, will actually pin processing to individual CPU cores. So imagine you have a 24-core CPU. You would end up pinning 6 or 8 cores to just handling TCP direct processing. And therefore, those cores are unavailable for other processing. And in the financial services world, we have to receive market data from exchanges. That market data comes in the form of multiple feeds. So there's a securities feed, and there is a separate fiber for an A feed and a separate fiber for a B feed. And in a perfect world, all of the information is duplicated on the A feed and the B feed. But the reason for the two feeds is to make sure that if there is a drop on one feed, then the necessary data will appear on the other feed. So that both of those feeds are received. The protocol processing and handling has to be implemented. The A feed and the B feed have to be arbitraged together into a single unique stream of information. And in the software network stack model, all of that is also happening on the host in software. So not only do we have 6 to 8 cores devoted to network stack processing, we have another 4 to 6 cores that are devoted to market data handling. So really, we end up in a world, in the traditional world, where 50% of the cores are devoted to just normal rudimentary operational processing, and therefore they're not available for the actual strategy processing that's being implemented on the host. Our model changes that entirely. So just one second, Vijay, just let me finish this. So our model changes that entirely by doing the network stack on the FPGA chip. We also support doing the market data processing on the FPGA chip. So essentially, all of that is happening on the FPGA chip, and an already processed unique stream of data is being delivered across the PCIe bus, allowing all of those cores to be reclaimed for the core strategies that people are actually implementing, or the core application processing that people are implementing on that server. Apologies. Nara?
Yeah. I said, just wanted to check the performance numbers, like the throughput rate, it says megabits per second. Is that correct? And CXL, like 1.1, and the post update, like latencies that you're measuring.
Yep.
What was the setup, or like how is it measured? Is it a simulation or?
Oh no, this is real flow. We don't really believe in hardware simulations. We like testing in actual silicon. So the way that we do this is we've got 2 FPGA boards. You'll see if you're at OCP next week, we'll actually have a live demo of what I'm showing you. So you will literally see this in person. So what we do is we have one FPGA board. Let me grab the right fiber. Implementing what we call Taser, which is again an sorry, this is just a tangle of fiber here right now, which is, as I said earlier, an FPGA testing tool. The only thing we use the PCIe bus for is to configure a test, start a test, stop a test, and offload the data. So imagine this is Taser. So we've got a 40G transceiver that plugs in, and this is actually a by-4 breakout. So this is really 4 10G fibers in the end. And what we're doing is feeding the fiber into a 50-50 optical passive tap, as you see here. Data comes in here, and then we're splitting. And then we have an outbound channel that goes to the actual testing target. But then we also are mirroring back to other fibers on Taser for the actual timestamping. So as you can see, same fiber type, this is OM4, it's the same fiber length, 2 meters. So since it's a 50-50 tap, we know precisely that the moment the data arrives at the target is the same exact moment the data is arriving back at Taser for timestamping. So essentially what that results in is that we can't account for the actual transceiver latency on the transmit to the target side. The timestamping is happening in the MAC. So literally the earliest point in the FPGA chip after the transceiver and PMA itself. So we get an inbound timestamp there. On the outbound side, we do the same thing in reverse, except for when the data is leaving, we're not timestamping there because we've got 2 meters of fiber to the tap, then another 2 meters of fiber back to Taser itself. So we actually have 4 meters of extra fiber latency, right? What we really want to do is to be able to timestamp right at the literally as the data goes into the transceiver and as the data comes out. So we have 4 extra meters of fiber on the outbound side. We absolutely benchmark the fiber. We can tell you, what the exact latency is of any piece of fiber that we use in our environment. And we could back out that 4 meters of latency, but we actually don't in our measurements. So our measurements are slightly more conservative, have slightly more latency than is actually occurring. One, we want to make sure that we are accounting for the unidentifiable latency of the transceiver on the transmit to the target side. And yeah, so we take care of that by allowing for 4 meters of extra fiber-induced latency in our measurement. But really, we're talking about 29 nanoseconds or so, roughly. of fiber latency in this particular setup. So that's baked into this. So what we're doing, as you were commenting on, the horizontal are different throughput rates. So 10, 15, 20, 25 megabits per second through, at least in this chart, 1 gigabit per second. We are sending 50,000 frames at each of those individual points. We could send more, we could send less. So it's 50,000 frames, and then we're communicating the 95th percentile latency of those frames. So each individual frame going to a target and coming back from a target is captured. We have an inbound packet capture file, an outbound packet capture file. There are nanosecond level timestamps and all of that. We subtract one timestamp from the other timestamp. Again, we're not backing out the fiber latency. And then we get the actual frame by frame IO latency for that frame. All of that goes into a database, and then we just do normal statistical analysis around all of that. We can communicate min, max, 50th percentile, standard deviation, however anybody might want to look at it. We test all of the products, not just ours, but any product of interest. We've tested the X2522 with a variety of network stacks. We've tested a variety of different NICs with a variety of network stacks. We've tested switches for port-to-port replication latency. Essentially, any network attached device or system can be tested as long as it can receive a message and ultimately transmit a message. And we just need a unique identifier in the inbound message and that same unique identifier in the outbound message so that we can relate the two messages to each other to make the calculation. So again, what we see here is PCIe 3 is slightly less than 1.4 microseconds in out, so it's about 1.38. I'll explain why that is in a second. PCIe 4 is, as we would expect, slightly better. PCIe 5, again, slightly better. And then CXL. So interestingly, what we've implemented is CXL Type 3, which is not officially validated in the Intel Xeon 4th generation CPUs, but we do work very closely with Intel. And ultimately, we worked with Intel CPU engineering and Linux host engineering to really look at the intra-CPU behavior with different CXL types. There are 3, type 1, type 2, type 3, and different CXL functions, CXL.io, which is essentially PCIe. CXL.cache, which allows us to put data directly into CPU cache, or CXL.mem, which is our actual implementation. So the post-Intel IP update is because at the moment we cannot run the PMA functions at 644. There is a little silicon feature that prevents us from doing that right now. So Intel is working on a fix for that. And with that fix, our estimated latency is the dotted line. Now, I'm going to come back to, I said that the PCIe 3 performance is 1.38 nanoseconds. So I think anybody who knows the FPGA industry would understand that Xilinx has a reputation for really, really, really low latency transceivers. And Intel does not have a reputation for really low latency transceivers. I can tell you that that is actually true. Now, the irony of this is the reason for the transceiver delta is that Intel, and prior to that, Altera, before Intel bought Altera, and maybe the future Altera, we don't know what PSG is going to be named post-spinoff. The strategy was to implement a chiplet tiled architecture. There are benefits to that. And the irony of this is a couple of weeks ago, I was interviewed by Forbes to speak about the benefits of the chiplet architecture. And there are many. Those benefits include being able to essentially custom configure an FPGA chip. If you want to have, for example, on the PCIe facing side, Intel has what's called an R-tile. You could have multiple R-tiles connected to the core die if you wanted, or you could have only one. That's the benefit of the chiplet architecture. You can define that. The downside of the chiplet architecture is that fusing creates a physical gap that is latency inducing. In non-financial services, single digit nanosecond sensitive implementations, that latency isn't relevant. But where really, really precise low latency and where really precise determinism comes into play, that gap is a problem. It introduces additional latency. And so I want to come back to that 1.38 nanoseconds. If we compare the Intel transceivers with PCIe 3, and we also have products that use Xilinx FPGA chips, so we are really knowledgeable about both Intel and Xilinx here. From a PCIe 3 standpoint, the Intel transceivers round trip, so going across the PCIe bus and coming back, are 386 nanoseconds slower than the Xilinx transceivers. And as you can see here, in a total round trip of very low microsecond latency, 386 nanoseconds is a significant percentage. So I'll show you another slide in a second. One of the benefits of the hardware network stack is we are able to process things much more efficiently with much greater determinism and much lower latency. Arguably, we are able to claw back a lot of the performance ground that the Intel transceivers lose. So that 1.38 nanoseconds includes a 386 nanosecond penalty. So if we implemented this on a Xilinx chip, our PCIe 3 performance is just about where our CXL performance is. But the Xilinx UltraScale Plus chips only support PCIe 4, not PCIe 5. And while we could implement CXL on a Xilinx chip, because it's only a PCIe 4 architecture, the overall throughput and bandwidth is more constricted, and the Intel FPGA chips are a better strategic move for us going forward. Then one other comment about the Intel chips. So again, they've got this chiplet architecture. However, Intel is working on a next generation FPGA chip that should be coming out roughly 2 years from now. That chip will be a monolithic die with integrated transceivers. And with that, there should be an Intel FPGA chip that equals or hopefully beats the Xilinx transceiver capability. So Intel is moving to equal its capability with where Xilinx is. Sorry, that has nothing to do with precision time. You get that info for free. Any questions on this before I go to the next slide? Okay.
You're muted, Ahmad.
Sorry?
Oh, sorry. So thank you for telling me. But so anyways, so we are on top of the hour. However,
sorry. Okay.
Nothing holding us up. We can continue going, but then you will lose a lot of audience because they might have like other things to do. So, I mean, we can keep going, and this basically the recording will be available to everyone and so on. Just
all right. Let me just go into the next slide. I'll do it in 60 seconds.
No, you don't have to rush. Again,
I'm happy. I'm happy to rush. I want to go home and have dinner. I've been in the office since 6:30 in the morning. I'm happy to go home. So the next slide is really trying to show what the difference is between a hardware network stack and a software network stack. So this tests the Xilinx 3522, which is an FPGA-based NIC that Xilinx SolarFlare released last year. But even though it's an FPGA-based platform, they still use the software network stack TCP Direct. The 3522 can support PCIe 3 or PCIe 4. We've configured it here using PCIe 3 so that we can compare it directly to the 2522 ASIC-based board, which is only PCIe 3. And you'll notice that we have also configured ÜberNIC to use PCIe 3. Would have been very easy to use PCIe 5, but then that wouldn't have been intellectually honest. And being really fair and really honest is actually important to us. So what we're showing here is a little microburst that happens all the time on securities exchanges during a trading day. Again, we did this with Taser. We started off with a really low rate of 25,000 frames at 300 megabits per second, which for exchanges is nothing. So the New York Stock Exchange, for example, around the market open can have a burst of 4 gigabits per second. Normal data rates on the New York Stock Exchange and NASDAQ are 850 to 950 megabits per second. 300 megabits per second is nothing. Then we have a very small microburst, 300 frames at 2.25 gigabits per second, and then we go back to the steady state. So what you can see very clearly is TCP Direct cannot maintain line rate at 2.25 gigabits per second. So all of the frames that are transmitted at that line rate are flowing into a software receive queue created by TCP Direct. And because it can't maintain line rate, those frames are just backing up upon themselves in the queue. And then the max latency comes out to a little bit more than 50 microseconds, whereas the normal steady state latency is, as I said earlier, about 1.26. So we get a massive spike in latency, as you see, and then the microburst ends. But because these messages are queued up in the buffer, and then they have to be released, they're not released once. It's frame by frame by frame that's actually processed through the TCP Direct network stack. So roughly the first 150 frames of the second steady state 300 megabit per second flow go into the receive queue behind the queued up microburst frames. So the point here is that the microburst in a typical software network stack lasts not just for the duration of the microburst event itself, but carries on beyond that. And if we actually looked at this frame by frame, we would see that the 300 megabit per second frames, the first one, has a latency of about 48 nanoseconds and then 45 nanoseconds, and it just decays across roughly 150 frames until it goes back to the steady state. And then we have on the right, ÜberNIC with a hardware network stack. So again, steady state 1.38. There's a bit of an uptick in latency to 1.89 microseconds, so we can call it 1.9, but it still maintains line rate. And the minute the microburst is over, the last frame of the microburst, and then the first frame of the 300 megabit steady state is back to the 1.38. This is tested on the same server, same CPU, same memory. The only difference here, even the tick-to-trade application is the same. The only difference is hardware network stack versus software network stack. So if you ever wonder what's the value of implementing network functions in an FPGA chip, here you go. Sorry, that was a little bit more than 60 seconds. That's it. If you're at OCP next week, come find us with the Meta folks. We'll have a live demo of all of this. We'll have PTM running, we'll have Taser running, we'll have ÜberNIC running with CXL. You can see it all functioning, and we can't show you the light on the fiber, but we can show you data ticking and graphs of data actually flowing. So I thank everybody for the time and for staying just a little bit late. And if anybody has any separate questions, don't hesitate to either send me an email directly or asking a mod to route an email to me.
Wonderful. Any questions before we close?
Yeah, I have a question regarding the White Rabbit support. I'm wondering what your approach to that is regarding White Rabbit. So do you want to, for example, do you want to develop support from scratch or use some existing IP or?
We're mostly going to be developing it from scratch. So I mentioned earlier, CERN is starting this official collaboration program. We are very likely to be the very first official member of that. We actually got the membership form and the contract today. They've been working, their legal's been working on that for a while. So as I said, I've already been to Geneva to sit down with them. We're gonna work directly with them to implement mostly from scratch. So there's not much available on the Intel architecture. The irony of this is we were showed, you know, when I was there, they showed me the actual very first White Rabbit device that was implemented on an Altera FPGA chip. But they moved away from Altera a long time ago. So the current IP blocks don't really support Intel. So there's going to be a lot of work that we're going to have to do for this.
Seth, one comment from the chat. Do you want to go through the other two slides as well and quickly see if there's anything?
There's not a whole lot. It's just more of a marketing plug for ÜberNIC as a whole. You know, we see a lot of value in CXL for not just communication of data for low latency and determinism, but we see ÜberNIC ultimately as a longer term strategic play as the heart of a high performance network IO, but you know, centrally managing point of an overall composable environment. So with CXL, we can create CXL bridging and switching, and we can actually then connect from a chip to chip or chiplet to chip standpoint, and we can route data from ÜberNIC across the PCIe bus from a physical and electrical standpoint directly to other CXL or other interconnect technologies without having to go across the CPU, the PCI bus to the CPU and then back. So we see huge value in ultimately this becoming the actual heart of an interconnected composable environment. So for example, imagine network IO here with a CXL bridge or switch connected directly to an NVIDIA GPU that's implementing NVLink C2C, and we can communicate directly from here to that board and back without having to go to the actual host environment. So it starts to create really powerful capabilities, bringing lower latency compute, storage, memory, etc. So there are lots of very interesting things that CXL will enable as that technology matures. And our goal is to be at the forefront of that going forward. And the last slide is just a comparison of different NICs. So that's it. Nothing terribly fancy and exciting, just trying to convince potential customers that our solution is a better solution. And we strongly believe that it is. So good example is, you know, the Xilinx 3522 that was released last year supports 10G and only 10G. That's it. Doesn't support any other link speed. So not terribly useful. In a world in which exchanges are implementing 25G internally, that board is no good for them. And for anybody outside of financial services, I mean, the rest of the world is on to much higher link speeds already. So some of these boards are useless to other industries because they're so narrowly focused. We could talk about it for a while.
All right.
Any other questions from anybody?
Great. Again,
Cool.
hearing none, will so thank you, Seth, for the presentation, and hopefully we see everyone else in 2 weeks for another call, which the title is Anomaly Detection in Raw GNSS Data by Maxim. All right.
Cool. Thanks very much, everybody.
Day, week. Bye, everyone.
Bye.
Bye.
しげさんお疲れ様でした。
お疲れ様でした。ありがとうございました。じゃあ、
はい、
来週お会いできるのを楽しみにしてます。
はい、そうです。はい、お願いします。
Thank you.
Thank you. Bye bye.